Okay, up to this point, we found the area of several different types of figures. We found what did we start off with? Like a parallelogram, right? Which included a rectangle, which includes a square, all kinds of stuff. It was just the base times the height. Then we did a triangle, which is 1/2 the base times the height. Then we did circles, right? Which was what? Off the top of your head, what's the area of a circle? Pi r squared. That should just roll off your tongue just like your name, okay? If I say area of a circle, you say what? Pi r squared, okay? It should be that easy. What else? We found the area of a sector of a circle, right? If we took a chunk out of a circle, and that was just whatever degrees it was divided by 360, pi r squared, right? And that, let's see, oh, we did a kite and a rhombus. What was a kite and a rhombus? 1/2, okay? On the quiz, some of you guys forgot the 1/2 on there, okay? It's 1/2 the product of the diameter, so d1 times d2. All right. So you do have a few formulas that you do have to memorize. So make sure that you review those. Keep those in mind. All right. Now what we're going to do is we're going to find the area of something crazy like this. What is this shape? It's a pentagon, right? 1, 2, 3, 4, 5 sides. It's a pentagon. It's not just any old pentagon. What do you think? Now I know you can't tell exactly from this, but just use your imagination. It's a what kind of a pentagon? A regular pentagon, which means what? We've talked about this a long time ago. What does it mean to be a regular pentagon? What's true about all the sides and what's true about all the angles? That's right, they're all equal. All the sides are equal and all the angles are equal. All right? We good so far? So what we're going to do is we're going to figure out, hopefully figure out, what the area of this thing is. I thought about, they give you a little description on why the formula is what it is. I'll tell you what, I think we have enough time. I started early enough today, so let's just talk about that real quick. Hopefully I won't spend a whole lot of time on that. Watch this. If we had a circle, I probably should have drawn this with a circle around here, but let's say this was the center of the circle, and this thing was inscribed in the circle, which means all the points of this. Actually, I might be able to draw that. Let's see if I can. Which one's a circle? That one right there. Okay. Let's see. How am I going to do this? Like that. Maybe make it a little bit bigger. So what I want to do is try to draw this. Whoops. Try to draw this circle. It's a little bit too big, right? So bring it in just a little bit. Move it over. Still just a little bit big. Let's bring it in just a tad. Say what? Yeah, I could make the pentagon a little bit bigger too, but I'm working with the circle. Or, yeah, pentagon. Right? Is that pretty close? Yeah, that's pretty good right there. Okay, so watch this. This is what they do on this thing. And then they... That blue line that I just drew right there goes to this circle. Well, pretend it almost hits a circle. Let's say it hits a circle right here. So this would be a radius of the circle, wouldn't it? Everybody with me on that? So what we're going to do is this. I'm going to draw this to all the vertices of that pentagon. So how many of these triangles am I going to have? 5 of them, that's right. And what's true, it does look like the Chrysler symbol, doesn't it? What's true about these two sides on this particular triangle right here? What do you think is true about those two lengths of those sides? They're equal to each other. Why? Because they're both the what of the circle, the radius of the circle. Okay, so they are equal to each other. So we have an isosceles triangle, don't we? So if I wanted to find the area of the whole entire thing, okay, the whole pentagon, watch what I could do. I could find the area of one of these triangles. And what do you think is probably true about 1, 2, 3, 4, 5 of these triangles? They're all the same, right? Okay, so they would be all the same, all congruent to each other. So if I find the area of one of these triangles, then what do I do to find the area of the whole entire pentagon? Multiply it by 6, exactly right. Does that make sense? Okay, so this is what I'm going to do. I drew this perpendicular, just like this, because this is my what? This is my height. And then this would be... right there, the length of one of the sides would be considered the base. Would you agree? Now this height is pretty important. In this triangle we call it the height, but in the pentagon itself, if I take the center of my regular polygon. I happen to pick a pentagon on this one. I could have picked a hexagon, could have picked an octagon, a decagon, whatever. Okay, I just picked a pentagon right here. If I take the center of this regular pentagon and I draw it perpendicular to one of the sides, would you agree that this height is perpendicular to one of the sides? Yeah, in order to be a height, it has to be perpendicular. We've talked about that. We have another name for this. And that height, instead of calling it the height of the triangle, I don't call this the height of the pentagon. I call it the apothem. O-P-O-T-H-E-M. I bet you that's a word you've never heard. Okay, we call it the apothem, or we just use the small letter A to represent this. So it's the apothem of the regular polygon. It's the height of the triangle, agreed? Okay, but in context of the whole entire pentagon, we call that thing the apothem. Alright, so there's a new word for you right there. That apothem is pretty important because it's important to find the area of this triangle. That height of that triangle is very important, so the apothem is important of that whole entire pentagon. Alright, so what would the area of this one triangle be? It would be 1/2 the what? The base times the height. Would you agree? But what would I do with that whole thing? Multiply it by, what do you think? That would be this one triangle, and multiply it by how many triangles? 1, 2, 3, 4, what? 5 triangles. So if I wanted to find the area of that whole entire pentagon, I could find the area of one of the triangles that's made, and then multiply it by how many triangles I have. Would you agree? So this would be the area of one triangle, times 2, that would be both of these, times 3, times 4, times 5. That's the area of the whole entire thing. So I could just say, multiply it by 5. Tell you what, instead of saying 5, let's be real general with this. Let's say n is the number of sides. So n is the number of sides. So what am I going to put right here? I'm going to put n. You follow me on that? This is an H, that's an N. Kind of look the same, except that's got a little thing on top, okay? So that would be our formula, basically, for really any regular polygon. This happens to be 5 sides, but I went real general with this. So you could say 1/2 the base times the height times what? How many sides that I have. All right? Here's another way to look at it. If I go 1/2 the height, and look at this b times n. This base, okay, times how many sides I have is what else that we've talked about on this regular polygon. If I take this base, multiply it by 5, or take the base and add it 5 times, base, 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 base. What did I just find? The perimeter, exactly right. So this base times the n is actually what of the figure? It's the perimeter of the figure, isn't it? So instead of putting bn, look what I can do. I can put p for perimeter. Now remember, we call this the height of the triangle. But when I talk about the whole entire pentagon or the whole entire right polygon, I'm not going to call it height. What did I say I was going to call it? Apothem, right. So I'm going to use A. So watch this. So here we go. Let's do this down here. So the area of a regular polygon. Now it has to be regular, which means all the sides have to be equal and all the angles have to be equal. This isn't just any old polygon. Okay, it's a regular polygon. So if you have the area of a regular polygon, this is what we're going to say. We're going to say the area equals 1/2. It's going to be right here basically. 1/2, and I think, how do they write it? I think they put PA or AP. They put AP. All right. Instead of height of the triangle, this is also the what of the pentagon. It's the apothem of the pentagon, isn't it? So instead of calling this the height, I could just call it A for the apothem. So watch, 1/2 times the apothem times the perimeter. Now, you may have been able to follow that. Maybe you didn't follow that. That's fine. I think we showed that pretty good on why this is my formula for the area of a pentagon. Now, this works for any regular polygon, not just a pentagon, not just 5 sides. This works for any of them. So there's another formula you need to memorize. You don't have to go through all this mess right here. You don't have to break it up into all the triangles. I mean, seriously, what if we had like 100 sides? Do you want to sit there and draw 100 sides and draw 100 triangles and then do all that mess? Of course not. That would be ridiculous. So we did it once with the pentagon, and so it just it just basically is the same thing for any regular polygon. Any regular polygon, this would be the area of that polygon. All right, there it is. 1/2 the apothem times the perimeter. Again, what's the apothem? The apothem is from the center of that polygon perpendicular to one of the sides. I could have done this. I could have drawn from here to here. That would also be the same thing, wouldn't it? That would also be an apothem, right? If it's perpendicular to that side right there, right? I could draw them all over the place. But if you have one of these from the center perpendicular to the side of the polygon, then that's the apothem. Make any sense? I think that was pretty good, don't you? Figure out where we got this formula from. Some of you guys don't care. Some of you would rather say, you could have saved 10 minutes, Mr. Hamrick, and just showed us the formula and just showed us how to use it and let us get a right answer. But that's not what it's all about, okay? It's more about trying to figure out where this stuff comes from. And every once in a while, we can actually show you where this comes from. Sometimes there's formulas that are really complicated that are not that easy to figure out where they came from. But on this one, I think it was pretty easy to see. All right, let's do a couple examples with this, and we'll see how to use it. Hopefully, it won't be too hard. Almost forgot to tell you, because they're going to ask you to do this a little bit. If let's say I started, I don't know, you can start anywhere. Let's say I started right here, and I was to take this angle, this one, this one, this one, this one, all the way to here. How many degrees is that whole thing right there? 360, right? So how would I find, just like, let's make this a little bit bigger. How would I find, let's say, just this angle right there? How many angles do I have? I got 1, 2, 3, 4, 5, right? Because I got 5 triangles, I got 5 angles right here. So that's right. So you would find that angle right there just by going what? 360 divided by how many angles I have, which is 5. Somebody do that real quick. Somebody do that. Who's got a calculator out? 360 divided by 5. 72? Is that right? Yeah, that sounds right. So 72 degrees. Because divided by 10 would be 36, and you double it, and that would be 72, right? Okay, so this angle right here would be 72. They call that the central angle. You know how you add a central angle of a circle? See how this is kind of related to a circle, isn't it? Because we have radius, we have a central angle and all that stuff. We have 360 degrees. Do you see how these regular polygons are kind of relate to a circle? All right, so that's how you would find that angle right here. So on this first problem that they give you, this example, here's the example. This is example 3 on page 793. The first question they ask you is to find, actually they just say find the area of the regular polygon. But unfortunately they don't give you all the information that they did. They don't just give you the apothem and the perimeter. That would be nice if they did, because what is the area of a regular polygon? It's 1/2 the apothem times the perimeter. Well, I could find the perimeter on this. The perimeter is not hard to find at all. So how would I find the perimeter? If I know one of those sides is 3, how do I find the perimeter? How many sides do I have? I got 6 sides, so it would be what? 3 times 6, right? So the perimeter, or the perimeter is 18. So that was pretty easy. So the perimeter, the distance around this whole thing is 18. What do I have to find though? I have to find this right here, the apothem. Give me the line segment that the apothem is right here. BD, good. BD is the apothem. I'll just call it little a right there. Is that all right? So what we have to do is we have to find little a. So how in the world am I going to do that? Well, this is an isosceles triangle. This is perpendicular. We learned a long time ago that it splits this base into 2 equal parts. So if the whole thing is 3, what is it from D to C? 1.5. Okay, so we know that. We don't know BC though, do we? All right, and we don't know BD. That's what we're trying to find. So what in the world are we going to do? I don't know a whole lot of stuff, but I could find this angle. Couldn't I? What did I just finish showing you? That's a central angle, right? It's from the center of the hexagon down to here like this. How do I find that big angle from here to here? Not by 5 this time. How many sides does this have? This has 6 sides, so it would have 6 triangles, right? If I kept on drawing all those triangles, I would have 6 of them. So it's 360 divided by 6, which is 60 degrees. Now this whole thing is 60 degrees. I'm not really going to use that whole entire angle, what do you think I'm going to use? I'm going to divide it by 2, that's right, to find this angle right here. So this would be what? 30. Okay, and of course this down here would be 60. Alright, make sense? This is actually kind of nice. Now what are we trying to find? We're trying to find this. I got a 30, 60, 90 triangle. Do you remember this? What's the relationship? You could just do a trig function right here if you wanted to, but since it's 30, 60, 90, I think it's a little easier to say what? That the long side, this is the long side because it's opposite 60, the long side is equal to what? Do you remember? Square root of 3 times the short side. That's right. Okay, it's the square root of 3 times the short side. Do I know the short side here? Yeah, I do. It's 1.5, isn't it? Okay, so what is the apothem then? I'll just draw it right here. So what's the apothem? 1.5 times the square root of 3. That's right. Now, I don't need to know what that actual number is, but because I'm going to take this and I'm going to take this and put it into this formula right here. Then I can use a calculator. Does that make any sense to you? I had to find the apothem, so I had to do a little trig to figure out what the apothem was. I could have done, look, I could have used this 30 degree and said opposite over adjacent, and I could have used the tangent and found that number, okay? Or I could have taken 60 and gone a over 1.5 and taken the tangent of that, all right? The tangent of 60 is a over 1.5. I could have done it that way because opposite over adjacent, all right? I saw 30, 60, 90. I remember back, you know, when I did this chapter on a 30, 60, 90. Yes. Yes, real quick. Okay, so so that's what I would use. Do you remember that? That the long side is square root of 3 times the short side? Yes? No? All right. If you do, it makes things a lot easier for you. If you don't, it's okay because you could always go back to the trig function and do a trig function. You would use tangent on this thing. All right. So now, how do we find the area of this? We just plug everything in. It's 1/2 times the apothem, right, which is 1.5 times the square root of 3, and then times the perimeter, which is 18. Plug and chug, put all that stuff in your calculator, and I hope you get 23.4. Somebody do that for me just to make sure. No, I didn't do that in my head. I cheated and looked in the book. Okay, so is it 23.4? All right, and that's... And the book does the same thing with this 1.5 square root of 3. If you look, they recognize it was 30, 60, 90, and they said, oh, let's just put it in there like this, and there you go. So that was a little tougher than them just giving you the apothem, giving you the perimeter. I mean, anybody could have done that, right? If I would have told you the perimeter, or even just one of the sides, and told you what the apothem was, then it would have been a piece of cake. The hard part about this is sometimes finding the apothem. Sometimes they give you the apothem, they don't tell you this length of the side. You're going to have to do some trig, maybe some Pythagorean Theorem or something to find the length of the side. So you're going to have to do a little work, a little bit of thinking to find out what's missing and what you're trying to find. Okay? In this case, you have to find the apothem on your own. Right, so you had to find that. That was the hardest part. Really, the hardest part about doing this problem was finding the apothem. In order to find the apothem, what did you have to do? You had to find that angle. They didn't tell you that angle, did they? So you had to figure out that angle. How in the world did I get that to be 30? Because I found that whole entire central angle by going 360 divided by 6, right? Because it's the whole circle, right? All the degrees divided by how many of these triangles I would have in here, which there's 6 of them. So 360 divided by 6 is that central angle. So this splits it in half because they're congruent triangles right here, and that's 30, that's 60, and you go from there. So there's several things you had to know from the past to be able to do this, okay, to find the apothem. The easy part was actually doing the area. All right, just plugging into this formula was the easy part. The hard part was trying to figure out what that BD or what that apothem was right there. So it took a little bit of thought, took a little bit of ingenuity. You had to remember stuff that you learned in the past, and then there you go. All right, if you got confused on that, go back on YouTube, watch it 2 or 3 times, all right, until you get it straight. All right, we got a couple more things to do. We're going to still do some area. I think we're going to get away from the regular polygon and just show you a couple things. It's not too hard. All right, look at this crazy picture. What we're going to try to do is find the area of this whole thing. All right, so we're going to find the area. Now, it's just not one figure. It's not like you're just going to have one formula, just plug it into one formula, then you're done. It's actually a combination of 3 different things, if you want to look at it that way. Actually, that should be should be brought in just a little bit. Sorry about that. That should probably be brought in about right in there somewhere. Okay, that's close enough. All right, so so here we go. We got to find the area of that whole crazy thing. Well, watch this. If I took this line and took it all the way over to the other end, what do I have up here? What shape do I have? It's a semicircle. Okay, so let's just work on that one right now. So let's just do the semicircle. Let's write it down. Semicircle. So what's the area of that? Well, it's pi r squared, what? Divided by 2, because it's half a circle, isn't it? All right, plug some stuff in. Pi, what's the radius of this semicircle? They tell you right there, it's 4. All right, square it, divide it by 2. What's that? 16, right? Over 2, which is 8, so that's 8 pi. We'll just hang on to that right now. We'll stick it into a calculator at the end. All right, so I'll tell you what, I don't want to circle. Let's put it in a box. So we'll hang on to that. That's the semicircle. So that right there is 8 pi. Good so far? What other kind of figure do you think you see in here? Okay, a triangle and a rectangle, I see. So if I took this, hopefully, and made it go up to here, it's actually supposed to hit right there at that dot, but you get the idea. Yeah, we got a triangle, we got a rectangle. Let's do the rectangle. Let's do the rectangle right in here. Just base times height, right? Which is 4 times 7. Do you see that? 4 and 7. So what's the area of that? That would be 28. So that's the area of that. Shouldn't circle it. What about this thing right here? This is it's a triangle. So I got a base and height, don't I? Well, I got a base is 4. I got to figure out what it is from here to here. Can I just guess? The whole thing's 7. Do I know anything? Not really, but I do know this is 5.7, so we'll call that x. How would I find that little x right there? Pythagorean Theorem, that's right, because I've got a right triangle here, and I've got 2 sides, so I do Pythagorean Theorem to find this. Okay, so it's going to be x squared plus 4 squared equals 5.7 squared. I don't have my calculator up, so Travis, you ready? Put some numbers in. So x squared is 5.7 squared minus 4 squared. Take the square root of all that. Travis, give me a number. 4.1. Okay, so that's 4.1. So how do I find the area inside this rectangle, though? It's base times height, so it's going to be 4 times 4.1, what? Divided by 2. I could do that in my head, couldn't you? 2 goes into 4, what? Twice. 2 times 4.1 is 8.2. So look what I have. I've got 8 pi, 8.2, 28. What am I going to do with all those? Add them all up. That's right. What is this? 25.1? Okay. So just add up those 3 numbers. Somebody do that. Who's doing that for me? Do you get around 61.3? Yes? No? 61.3? Is that right? Okay, good. That's what the book has, so that's good. Area is 61.3. And it's square whatever. I don't know what it's even in. We'll call it centimeters. Okay? And there it is. That's how you do that. Now, that's by addition. Now, you could have done this. We don't have enough time to do this, but you can look on your own to this. There is a thing you can do by subtraction. You could find the area, like if I wanted to do this. Watch. If I wanted to bring this straight down and this straight down right here, and then subtract this from the whole thing, find the area of the whole thing, take this away from it, you could find it that way too. Look in the book. There is an example on that. We're just running short on time. Sorry we weren't able to get to that. That's not that big of a deal. Most of the time you could do it like this. All right, but there are times you can do it by subtraction. So let's do some problems, huh? So let's do, this is section 11.4. And let's start on page 796. So 796. Let's just go. Let's go 10 to 24. Okay, so it's 796, 797 actually. All right, and we're going 10 to 24. There we go. This is probably the next to last, not probably, it is, the next to last brand new lesson that we're going to do all year. We got one more lesson to do, 11.5, and we will be done doing brand new lessons. Okay, we'll take a test. I'm thinking that we could probably take the test on Friday. Normally, I don't like to give a test on Friday, but we're running short on days to get this done. So, test on let me say this again. Test on Friday on chapter 11. All right, and we'll just do corrections on Monday. So, if everything works to plan, we'll probably take the test on Friday. All right, that's it.